My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 579. In this lecture, we will try to understand gradient monitoring and clipping. We train multi-layer perceptron. Or any deep learning model for that. We should monitor the gradients. Because the most important part of any optimization strategy is about gradients. The whole game is about gradients because gradients are what we use to update our weights. We use gradients to update our weights. We basically use gradients, isn't it? So let's assume let me assume you have neural networks like this. This is your input layer. You have bunch of inputs in this input layer, xi1, xi2, so on. You have layer 1. Let me say this is layer 1 and this is fully connected. Let's assume a bunch of neurons here. In L1 you have bunch of neurons, isn't it? Then layer 2, again I have layer 2. This is also fully connected. Layer 2 is also fully connected, and then I have my output layer. Let me assume this is my output layer. Let's say this is my output layer, isn't it? So given an input xi, output is yi cap. What is the input here? Input is xi and output is yi cap. This is my model. So what you should look at it. You have bunch of your weights here. Let me say w power 1 is a bunch of weights, w power 2 is a bunch of weights here, w power 3 is also a bunch of weights. So the suggestion here is, what I mean, gradient monitoring here. It's a good habit to monitor your gradients for each weight, isn't it? It's a good habit to monitor your gradients for each weight. What I mean by update here is, so we have what is our wt equal to wt minus 1 minus something. This something could be complex based on the algorithm we are using. What is this something? We are using, if you are using very simple SGD or mini batch SGD, this could be eta into g of t. This is a whole term. This whole term is update, because this is what we are using. If you are using Adagrad or there is stuff, it is slightly more complex, but in a nutshell, we are changing from wt minus 1 to wt using this update, isn't it? So you should always monitor. This is update. Eta into g of t is update, isn't it? You should always monitor your gradient and update your you should always monitor your gradient, update you should monitor it for each epoch, isn't it? You should monitor it for each epoch. For each epoch you should monitor it. Also you should monitor it for each weight and for each layer, isn't it? This monitoring is very useful to detect problems like vanishing gradient, isn't it? Vanishing gradient happens more often in the early layers, isn't it? Vanishing gradient happens in the early layers, because what happens that the weights that are here for final loss function, where it happens, just understand this part. What it says here, it happens. That's what it says. Vanishing gradient happens more often in the early layers. Here only it happens, isn't it? For the whole weight to back propagate. Actually, we are back propagating here, isn't it? We are back propagating. From here, you keep on back propagate. Yes, you keep on back propagate. Yes, because there are lots of multiplications of derivatives, and all of them less than 1, you might end up with a vanishing gradient problem, isn't it? You must vanishing gradient problem for weights in this region. Yes, you must end up with the vanishing gradient problem here. In this region, you might end up you might end up with a vanishing gradient problem for the weights in this region. Which region? In W power 1, isn't it? Not so much weights here. Yes, not so much weights here, isn't it? At W3, and hence you should always monitor your gradient in the whole update itself. Better to monitor gradient in the whole update itself. What is your Wt equal to Wt minus 1 minus eta into g of t. This whole term, which is called update term, isn't it? Which one is the update term? Wt equal to Wt minus 1. What is this? What it says? Vanishing gradient problem for weights here. Yes, here that's what I'm saying actually. Here you will come across vanishing gradient problem for weights here. Yes, while back propagating you will come across this one. Yes, not so much of you may not face vanishing gradient problem here, isn't it? That's what it says. Yes, Wt equal to Wt minus 1 eta into g of t. Whole update itself. What it says, you should always monitor your gradient in the whole update itself. My update equation, Wt equal to Wt minus 1 minus eta into gt. This whole term, which is called update term for each epoch, isn't it? You should always update term for each epoch. You should monitor it for each weight. You should monitor. You should also monitor for each layer, isn't it? And when gradients becomes too small, especially in the first few layers, that could indicate that you have vanishing gradient problem, isn't it? And if the gradient becomes very large, you could be run into the exploding gradient problem, isn't it? You could be run into the exploding gradient problem when the gradients becomes very large, isn't it? Because you have to monitor this to understand what is happening. Yes, if you detect vanishing gradient problem, if you detect vanishing gradient problem, you should immediately change your activation function to ReLU, isn't it? Activation function to ReLU if you are using something like sigmoid or tanh, isn't it? Gradient clipping is very interesting idea which is used to avoid or to get rid of exploding gradient. So the solution to the exploding gradient problem is gradient clipping, isn't it? In the gradient clipping is very, very simple and elegant solution. Imagine I have lots of weights Wkij. Let me assume I have weights Wkij. If I place all of my weights in a single vector W, let me call it as W. W is basically all my weights in my network. So the idea here, when you want to perform gradient clipping, the core idea is this. If you think W as a vector of weights, your weight vector, you can also think gradient as a vector, isn't it? Gradient means I can say dou L by dou W1 1 dou L by dou W1 1 2 dou L by dou W1 1 3, like this, isn't it? Let's call this gradient vector as G, isn't it? Let me call it as capital G. So if you have exploding gradient problem, suppose let's say I have gradient with value 200. Let me say gradient with value 200. Let's say dou L by dou W321 is 1000. Let me assume. So when you have a gradient which is very large, one thing that when you have a gradient which is very large, one thing that we can do is gradient clipping. Concept is, what is the concept? The new gradient vector G nu equal to G by norm L2 norm of G into tau. What is this tau? Threshold. This is tau is threshold, norm G means this is L2 norm, isn't it? The gradient clipping strategy is called L2 norm clipping, isn't it? This strategy is known as L2 norm clipping. Now, when I have vector capital G, let's assume I have vector capital G here. Let's assume I have values something like, let it be 2, 5, 10,000 and 0.5, so on. When I divide G with its norm, all these individual gradients will become less than 1. Isn't it? All these individual gradients will become less than 1 because the norm of G is greater than all of these things. Norm of G is greater than 2, 5, 10,000, 0.5, isn't it? It's greater than all of those values. This is L2 norm. We know that what is L2 norm? What is L2 norm? Under root of G1 square plus G2 square plus G3 square plus so on. L2 norm of G is greater than all of these individual terms, isn't it? When I divide each of these terms with the norm of G, with L2 norm of G, each of these values are going to be less than 1, isn't it? And then I am multiplying with the threshold tau, isn't it? What I am doing here, I am multiplying with threshold tau. Suppose if my tau equal to, then finally my G nu, all my gradients in G nu vector is less than or equal to tau, isn't it? So this is called L2 norm clipping, because what are we doing here? We are using the L2 norm and we are using the tau. Basically says all the gradients are less than or equal to tau, and we are using L2 norm to enable that, and hence it is called L2 norm clipping. This is readily available in most libraries. So whenever you have exploding gradient problem, the simplest way, there are other strategies also, the simplest way is L2 norm clipping strategy to ensure that none of your gradients are too large. Very simple thing, but as a rule of thumb, always monitor your gradients and keep looking for what's happening. You should monitor your gradients. And also updates to see if you are running into vanishing gradient problem or exploding gradient problem or some other problem. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.